I'm going to start off with this synthesis that we left off on Wednesday with. So taking a look at it, there's no real way to just insert a carbon here. Just like I gave you guys the hint, MCPBA, you're basically going to have to burn off this entire group and add a new one. So if I throw in MCPBA, I've got tertiary center here, primary center here. So the oxygen should insert on the tertiary center. This lets us basically remove this entire group here. We add in water and acid. Whoops, H3O plus. Now we just need to add this larger carbon group to it. So a couple of different ways you could do this. You could reduce and do an oxidized Grignard kind of a thing. I'm going to throw in SOCl2, make the acid chloride, and then do our soft alkylating reagent, which would be Li, and then the group we want. So that, because we want to add this isopropyl group to it. All right, I'm going to spend the most of today talking about NMRs. I'm going to get you guys go through a bunch of them. I'm kind of going to give you just kind of a review of different concepts, and then I'm going to put the NMRs up and let you guys do them. So the actual NMRs, if you want to grab them now, are under files, lecture notes, and something like carboxylic acid esters, NMRs. That was the only thing in the lecture notes that starts with the word carboxylic acid. So as a review, if I have a carboxylic acid, as well as an alcohol, I'm going to get a little broad peak. That looks like this, depending on where it is. If it's in the 10 to 12 range, it's going to be a carboxylic acid. If it's in like the 2 to 6 range, it's going to be an alcohol. So really far down to the left, you get one of these peaks that's going to give you a carboxylic acid. I think your book says 11 to 12. Sometimes it's a little bit less. The other side of your carboxylic acid is just a normal carbonyl. So these H's over here are going to be in the 2 to 3 range. Kind of similar, but a little bit distinguished from if we had an aldehyde. So our aldehyde peak's going to show up between 9 and 10. These H's are going to show up between 2 and 3. And this is directly bonded. This H here is directly bonded to our carbonyl, as opposed to the one on the oxygen, or the carboxylic acid, where you have carbonyl, oxygen, H. So this is actually going to give you like a neighboring signal peak. So this has 2 neighbors to it. This would give you a triplet versus our carboxylic acid, which just gives you a broad peak. Okay, so esters are kind of a combination of a aldehyde and an ether. So for an ether, these H's show up in the 3 to 4 range. So if we think about what an ester is, on one side, should be the side of the left here, we have an oxygen attached to it. So this is basically just this half of an ether. So these H's are going to show up in that same 3 to 4 range. Versus your other side, your right side here, you're one attached to a carbonyl, which is the same thing you have over here. So these are going to show up in the 2 to 3 range. So an ester is basically just these two concepts squished together. All right, let's talk a little bit about multiple substituents attached to the same thing. So if I think of just a normal carbon chain, these are normally in the 2 to 3 range, or sorry, 1 to 2 range. These are just regular CHs. If I throw a carbonyl on there, this puts me in the 2 to 3 range. Or let's say an aromatic ring, same concept. You can think of these as being 1 ppm larger, like 1 to 2, you were to say plus 1 to that, you get to 2 to 3. You basically just added 1 here. So 1 goes to 2, 2 goes to 3. You're in this range. You think of like an ether. These are in the 3 to 4 range. So if you wanted to take this, you could think of this as being 2 units higher. So we're calling this a plus 1 because we're in the 2 to 3. 3 to 4 range would be a plus 2. I could make an entire chart about this. So 1 to 2 range would be, I'm gonna call it plus 0. 2 to 3, plus 1, 3 to 4, plus 2, 5 to 6, plus 3 here. We can kind of use this when we have multiple substituents. So let's say we have this here. So on the left side of it is a carbonyl, which would be this kind of like plus 1 range. So we're calling that. On the right side of, I got a better marker. See if this will. We have attached to an oxygen here. So we would call that a plus 2. Oh yeah, I think I said this should be 4 to 5. Sorry, not 5 to 6. I went too much. So that would give us a total of plus 3, which is going to put this over here in the 4 to 5 range. And you can kind of use that as like a combination to do these. So if I had, let's say, a double carbonyl here, this carbonyl side would normally give me 2 to 3. This one also 2 to 3. Those are both like plus 1s. So it's going to give me a total of plus 2. And this is going to end up in the 3 to 4 range. It's another way if you guys want to think of it like this. I kind of like it. It tends to be kind of a little easy mathematically. So when you start seeing things with multiple substituents on it, it's going to give you two different, or just gives you a way to kind of calculate where it's going to roughly end up. Okay, I'm going to throw up some NMRs, let you guys kind of work through them. So we'll just kind of do them one at a time. Let's start with this first one. I'm going to give you guys about 2 minutes to work through this one. Should be pretty quick. I'll zoom in on it, write out some peaks for the ones that are hard to see, and then we can go through them together. So get started on this one. 5. All right, this one should be pretty straightforward. We got a carboxylic acid. This little peak down probably around 11. So let's start by question in the chat. Yeah, I'm gonna post the book problems and the practice problems during office hours today. So should see them show up probably around 1 o'clock today. I'll do 20 and 21. Okay, so starting with this carboxylic acid, peak that is next to our carbonyl here is going to show up in the 2 to 3 range. This one should be pretty straightforward. So it's going to be that CH. That's in the correct range. It's supposed to have 4 neighbors. Currently has 0. So that'll be a CH and a CH3. Our CH3 is supposed to have one neighbor, which makes sense. Our other CH is supposed to have 7 neighbors. Currently has 1 from the other CH, so the other 2 CH3s should get you here. Do some assigning. A, B, C, D, E here. A is going to be our carboxylic acid. B is our one that's next to the carbonyl, CH next to the carbonyl. C is our CH not attached to our carbonyl. D is our CH3. E is our 2 CH3s. All right, take a few minutes, go to the next one. You guys should have everything you need to fill that out. I'm gonna write in the integrations while you're doing it. Not integrations, the peak numbers. Okay, let's take a look at this one. We've got 2 oxygens in solution. We got a peak roughly between 3 and 4. It's a little higher. We got a peak between 2 and 3 here. We most likely have an ester. We don't have a carboxylic acid. We don't have 2 alcohols. We don't have an aldehyde. We shouldn't have 2 ketones. So let's see. Drawing in an ester. Our side with our oxygen should be this further down range. So this would be this 2H here. So we can draw on this CH2. We've got this peak between 2 and 3, which is also a CH. It's supposed to have 6 neighbors, so we can draw those 2 CH3s on there. Other CH2 is supposed to have 3 neighbors, so that'll be other CH3, giving us this structure. So A, B, C, and D here. A is going to be the one attached to the oxygen. B is the one on the other side by the carbonyl. C is our CH3. And then D would be our two symmetrical CH3s. All right, take a minute to go through the next one, maybe like 5 minutes. This one is probably the hardest one that we're going to talk about today. Someone asked me a question in the chat. I'm going to explain that after we do the next one. So take about 5 minutes to go through this one, see if you can figure it out, and then we'll go through it together. Let's get started on this one. So peak between 6.5 and 8 is going to be an aromatic ring. It's got 5 H's on it, which means we only have one open spot. We've got 2 oxygens in solution. We should have 10 carbons. Our aromatic ring is going to give us 6, 7, 8, 9, which means we have a missing one, which is probably a carbonyl, which also makes sense because we have this singlet here. So I'm going to draw out the product, and then I'm going to kind of walk through why it is that, and then I'm going to draw out some alternatives and explain why those don't work. So this peak that's really far down is most likely attached to the aromatic ring as well as the oxygen of an ester. So if I was to draw it out, it would look CH2, O, ester here. And then the other side of our ester is going to be this 2 to 3 range peak, which would be a CH2 followed by a CH3. Let's assign them, and then I can go through some other answers I've seen a lot for this one. So A, going to be this whole aromatic ring. B, carbon next to, between the aromatic ring and our oxygen. C would be this other CH2 here. D would be our last CH3. Okay, the first one I get a lot is, why is this not this? And this is going to all come down to peaks. And this singlet here. So if I take a look at this, or I could have the oxygen and the carbonyl switched, either way. This here is going to be next to 2 neighbors. So this would give you a triplet. This one here would be next to 6 neighbors or 5 neighbors. So it would be one more, would be a sextet. This one here would be next to 2 neighbors. So this would be a triplet. That's why we don't get this pattern. It's because of our integrations, they don't make sense, or our peak numbers, they don't make sense. We have a singlet, triplet, or a quartet, and a triplet here, which we can't really get based off of. We can't get to this structure here. The other one, which is a little bit closer, I get asked why it isn't, is this one on the right, which is pretty similar. And honestly, you'd get most of the points if you drew this. The difference is really going to come down to that thing that we were talking about earlier, which was the +1, +2, +3 kind of a thing. I'm going to redraw it out on the left. Oh, gravity's supposed to be +0. 4 to 5. So if I think of my normal attached to a carbonyl, these H's are in the 2 to 3 range, which we're calling a +1. If I think of my normal attached to an aromatic ring here, it's also in the 2 to 3 range. Sorry. CH3. So we also said that was in the 2 to 3 range. We have both of them right here. So we have a carbonyl. We also have this aromatic ring that's attached to. So this has both of these. So you could add them together and say that this would be in the 3 to 4 range. So that'd be a total of +2 if you were to add those two together. So this signal here should show up between 3 and 4. This one here is directly attached to an oxygen, so this should show up in the 3 to 4 range. Versus if we look at what we have, you have both the oxygen, which would be a +2, and the aromatic ring, which is a +1. So this should show up all the way down between 5 and 6, or 4 and 5, which is where it is. It's a little bit past it, but for the most part. And then this one's just attached to the carbonyl, should show up between 2 and 3. So if these two peaks were pushed into this 3 to 4 range, that would actually make this compound. But because they're separated out, that's why you're going to get this configuration here. Okay, I'm going to give you guys a little bit of time to do the last one, which should be easier. I'm actually going to move a peak because I'm not sure what's happening in this. So slide this down over to here in the 2 to 3 range, which is what it should be. I'll zoom back in. So this should be 7, and it should be between 2 and 3. I don't know why it's pushed all the way down here. So take a minute to go through this one. Should be a little bit simpler. We'll talk in about 2 or 3 minutes on it. All right, so we got peak between 6.5 and 8. This is an aromatic ring. It's got the 2H. It's really nice symmetrical 2 peaks, so it's just gonna end up at this para position. We've got a peak way down to 12. This is our carboxylic acid. I shifted this peak down to 2 here. It's got 7 peaks, should be, and it's next to a 6H. So most likely these are going to end up on other ends of our carboxylic or our aromatic ring here. So throwing the carboxylic acid on one side, and then this CH on the other, will let us fill in the last 3 positions here, which would be just these CH3s. All right, so we'll do some more aromatic NMR or some more carboxylic acid NMRs when we start reviewing for the exam. Let's do a little bit of chapter 20 today. I'm going to talk about maybe one reaction, 1 or 2 reactions, and then I will let you guys go. So chapter 21 is all about enols and enolates. So what an enol is if you take a ketone or an aldehyde, throw in H3O plus, we can pick up a proton, protonate our carbonyl, water can come in, pick off this. You call it a beta proton. It's 1 away from our carbonyl. And we're going to generate this, which is called an enol. We also can make enolates. Oops. All right. Which is going to use base. We're going to do the exact same concept. We're going to pull off this H here. Except now we're not protonated. And we're going to make what's called an enolate. And generally when you see H, like a carboxylate, this just means it's negatively charged. So there's some reactions we can do with these. I'm going to do one of them today with both the enol and the enolate. Let's start with the enol one. And we're just going to halogenate it. So if I take cyclohexanone here, throw in H3O plus, in Br2 or Cl2. We can pick up an H here. Our water can then pull off a proton. Give us our enol. And then from here we can brominate. So the 2 electrons from our oxygen can come back down, reform the carbonyl. This double bond will do an attack. We will make this protonated version of our final product, and then we'll lose that H plus 2 brominate here. All right, we can also do this with base. It'll be very similar. So throwing in, let's start with NaOH as a base. In Br2. So we could pull off one of these protons. In this case, we're going to generate an enol 8 because it's negatively charged. This will attack one of our bromines again. So electrons can come down, reform our carbonyl, double bond will come in, attack the Br. And again, we'll brominate on this same position. So both of these reactions we did with small bases. If I take something a little bit more unique or less symmetrical. So now we have 2 different hydrogens or protons you can pull off. We've got a tertiary position. And we've got a secondary position here. NaOH is a small base. Which means it's going to pull off that tertiary proton, and that's where it's going to halogenate. So this is going to lead to this bromination product. Versus if we did this with a large base. Like let's say LDA. Which is this lithium diisopropylamine. followed by VR2. Because this is so large, it's going to selectively pull off that less sterically hindered center, which is the secondary center, and we are instead going to brominate on the left here. So following the same normal rules as we did, small base is going to pull off the more substituted center, large base to pull off the less substituted center, and our product is going to follow suit. All right, I'm going to stop here. On Monday, we will go pretty far into chapter 21. So I will see you guys then.